Alright, welcome back everybody. This is chapter 2 on the cosmic perspective, discovering the universe for yourself. And so here in our first image we have a picture of some star trails. I don't know where this is, maybe Arizona, with the red rocks there. And what you see in the middle of that formation is the pole star Polaris, the North Star. And probably a 5 or 6 hour long exposure here of the stars. And they all go around the pole star. If you take an imaginary line from the North Pole of the Earth and go straight up into the sky, you would run into Polaris, and everything rotates around that because of the Earth's rotation. Well, what are our goals for this chapter? We're going to look at what does the universe look like from Earth, why do the stars rise and set, and why do the constellations we see depend on latitude and time of year. Latitude is our position on the Earth between the North and South Pole. So what does the universe look like from the Earth? With the naked eye, we can see more than 2,000 stars, as well as the Milky Way, our own galaxy. You might think, well, there's a lot more stars out there, and that's true, but most of them are pretty far away and pretty faint, actually. So here we see the Milky Way galaxy, and you see gas and dust. The dark stuff in that band of light is not an absence of stuff, it's just the dark dust blocking the starlight. If we took away all the dust in the galaxy, you could actually read a book by starlight at night. Well, what is a constellation? A constellation is a region of the sky, technically, and there are 88 constellations in the northern and southern hemisphere. Now, you've heard of constellations like Orion, and that's a nice big one out in the winter sky. Constellations are not only just the formation of the stars that make up a figure, but it's actually a kind of like a state boundary or an area code or a county map. The sky is broken up into 88 chunks that we call constellations, and everything in that chunk, just like everything in the state of Missouri belongs to Missouri, everything in that space of sky belongs to that particular constellation. Here's the concept of what we're going to hear about now is the celestial sphere. This is an imaginary model. A model is a way of looking at stuff in science to get a better picture of it in a simpler way. So the celestial sphere is our model of the sky. It's kind of like the Earth imagine the Earth with a plastic globe around it, and on that plastic globe is all the stars and all the constellations and all the planets. So stars at different distances all appear to lie on the celestial sphere. We make that adjustment just for simplicity. And the 88 constellations are all over the celestial sphere. Now, we're going to make a definition here. This is called the ecliptic. And so this line you see here on the celestial sphere is called the ecliptic. It is the sun's apparent path through the celestial sphere. And it is tilted 23.5 degrees to the equator of the Earth. That is because of the tilt of the Earth is 23.5 degrees. Just like we have a North Pole and a South Pole on the Earth, we also have a North Celestial Pole and a South Celestial Pole on the celestial sphere. We also have an equator on the celestial sphere, and this is simply the equator of the Earth projected out into space. The Milky Way is a band of light making a circle around the celestial sphere. So this is our view into the plane of our own galaxy. Our galaxy is a flat disk with a bulge in the middle. It looks like a soft fried egg. So here's a picture of our galaxy, the Milky Way. It looks like a hurricane. I've always been fascinated by how these spiral galaxies like ours look a lot like hurricanes. And so we're off, not in the middle, but actually out in one of the arm bands of the Milky Way galaxy, and we look out in all different directions. We actually can't see the other side of the Milky Way because the center here probably has a black hole inside of it, and there's lots of gas and dust, and it obscures our vision of the other side. Let's look at our local sky. We're going to look at objects' altitude. This is how high it is above the horizon. And the direction specifies its location in your local sky. So if you would look straight overhead, you'd be looking at a point we call the zenith. And that is an altitude of 90 degrees. From your horizon to the straight above point in your sky is the zenith at 90 degrees north. The meridian is an imaginary line that passes through your zenith, that point straight above your head, no matter where you are on the earth. And it's not the North Pole unless you are at the North Pole. The meridian is a line passing through the zenith, and it connects the north and south points on the horizon. Now, this is a nice little way to measure stuff in the sky with angles, just like we do in geometry. We have a way of using your hand to kind of measure how big things are in the sky. So if you take your thumb and you hold it out in front of you and try to block something, it's about 1/2 of a degree. Now, we probably know that there are 360 degrees in the entire circle of the sky. So your thumb is about 1 degree. I want you to try this someday. I want you to go outside at night, try to block the full moon or block the sun with your thumb and see what you find. I bet you can do it because the sun and the moon are all both about 1/2 of a degree in size, in angular size in the sky. If you hold your fist out, that's about 10 degrees, and a full hand width is about 20 degrees. So here are those angular measurements. Full circle is 360 degrees. 1 degree has 60 arc minutes. Think of it as a clock, like time. 1 degree is 60 arc minutes of angle. And then every arc minute has a arc second, and there are 60 arc seconds in an arc minute, 60 arc minutes in a degree, and 360 degrees in the whole sky. Why do the stars rise and set? Well, the Earth rotates from west to east, and so the stars appear to circle from the east to the west, since we're opposite of the sky on the Earth. Now, there are stars near the north celestial pole, and they never set below the horizon. They're called circumpolar. There are stars near the south celestial pole that we never see in the United States. All other stars and the sun, moon, and planets rise in the east and set in the west. Let's repeat that one more time. Everything in the sky rises in the east and sets in the west. The sun, the moon, the planets, and the stars. Why do the constellations we see depend on latitude and time of year? The reason is because they depend on latitude because your position on Earth determines which constellations remain below the horizon. They depend on time of year because Earth's orbit changes the apparent location of the sun among the stars. So you know the Earth goes around the sun. That's called revolution, which is different than rotation, which happens daily. It takes 24 hours roughly to rotate once. It takes 365 days roughly to go around or revolve around the sun. Now, the pole star Polaris is at a certain altitude above your horizon. And in fact, it's the same number of degrees above the horizon as your latitude on Earth. And so, let's use Springfield, Missouri for an example. We're at about 37 degrees north latitude. So we are 37 degrees north above the equator. And so Polaris, the pole star, is exactly 37 degrees above your horizon. It's kind of a Boy Scout trick. If you ever get lost camping, you can kind of figure out where you are by how high the North Star is. Now, on the Earth, we have latitude and longitude. Latitude is the position north or south of the equator, and I said we're about 37 degrees north latitude. Longitude is the position east or west of what we call the prime meridian, which runs through Greenwich, England. And it actually goes through the Old Royal Greenwich Observatory, which is near London, and it marks the prime meridian. It's the starting point for just like the equator is the starting point for north and south, prime meridian is the starting point for east-west. And Springfield is about 93 degrees on that, west. The sky varies with latitude, but not with longitude. Here's what I was saying about the pole star. However many degrees above your horizon the pole star is marks your location on the Earth. Now, how do we find the pole star? Well, we can look for the Big Dipper. Now, the Big Dipper is not actually a constellation. It is what we call an asterism. It's a part of a constellation. The main constellation of that is Ursa Major, the Big Bear. Well, what we can see here in the Big Dipper is the handle of the Dipper and then the bowl of the Dipper. And those last two stars in the bowl of the Dipper point to Polaris, which is actually part of the Little Dipper, Ursa Minor. The sky varies as the Earth orbits the Sun. And so as the Earth goes around the Sun throughout the course of a year, the Sun appears to move eastward along the ecliptic. So we know, to kind of summarize here, we know that we see about 2,000 stars and the Milky Way, which is 200 billion stars, with our naked eyes, and each position on the sky belongs to one of just 88 constellations. We can specify the position of an object in the local sky by its altitude above the horizon and its direction along the horizon. The stars rise and set because of the Earth's rotation. Why do the constellations we see depend on latitude and time of year? It's because your location determines which constellations are hidden by the Earth. There are a lot of constellations in the southern sky that Australians can see that we never see. Likewise, the people in Sydney, Australia never see the Big or Little Dipper from their location. And the time of year determines the location of the Sun on the celestial sphere. We see the big constellation of Orion the Hunter in the winter and early spring. We don't see it in the summertime because the Earth is in the way of the Sun. Now let's take a look at the reason for seasons. What causes the seasons? How does the orientation of Earth's axis change with time? Here's a true or false question for you. Earth is closer to the Sun in summer and farther from the Sun in winter. Is that true or false? I'll give you a minute to think about that. We're warmer in the summer, but when we're warm in June, Australia is cold in the wintertime. So which is true or not? It's actually false. Seasons are opposite in the northern and southern hemispheres, so the distance cannot be the reason. The real reason for seasons involves the Earth's axis tilt, which is about 23.5 degrees from parallel. Now the difference is slight. In the summertime we are about 94 million miles away, and in the wintertime we're about 91 million miles away. And we use an average about 93 million miles. But that small 3 million mile difference is the similar difference as if you had a campfire outside and you were 30 feet away from that campfire, and then you moved in 1 foot closer. You put your hands out and you try to feel that extra heat. You're not really going to feel much extra heat with that. That's the difference. So the seasons depend on how Earth's axis affects the directness of sunlight. Direct light causes more heating. The axis also tilts the directness of sunlight during the year. We get our most direct rays in the northern hemisphere on the first day of summer, June 21st. The sun's altitude also changes with the seasons. In the summertime, the sun is higher up in the sky and we get more direct sunlight. In the wintertime, the sun is lower in the sky and we get less direct sunlight. So the real reason for seasons has to do with the Earth's axis and its tilt relative to the sun. Summer occurs in your hemisphere when sunlight hits it more directly, and winter the opposite when it's less direct. And so the axis tilt, 23.5 degrees, is the key to the seasons. Without it, we would not have any seasons on Earth. So why doesn't that distance matter? As I already explained to you, it's about a 3% variation. The variation of any season on any hemisphere. The sun's distance is even a smaller difference. So it's just a very small difference that doesn't really matter in the scheme of things. So we have 4 particular points on our orbit around the sun that we mark the seasons with. The summer solstice is in June, the winter solstice is in December, and solstice means equal light, about the same 12 hours sunlight, 12 hours daylight in a time. Excuse me, solstice, that's the equinox. Solstice is when you have the most amount of light or the most amount of darkness. It's the spring and fall equinoxes that we have in March and September. That means equal, and that's when the sun is directly overhead the equator of the Earth. So we get equal day and night. Sorry for that. We can recognize the solstices and equinoxes by the path of the sun in the sky. So we already said that it's higher in the summertime, it's lower in the wintertime, which adds to our temperature fluctuation. Now, we've already mentioned that it's the tilt of the axis of the Earth that causes the seasons. But the tilt of the Earth's axis actually changes over time. And we do this wobble, kind of like a spinning top. Like a kid's toy would wobble over time as you spin it. The Earth wobbles also. And so we go around this 26,000-year orbit called precession. And so there are times that Polaris is not the North Star. In fact, most of the time it's not. In a few thousand years, another bright star named Vega will be the North Star, and the sky will look different. Let's look at the moon, our constant companion, for a minute. Why do we see phases of the moon, and what causes eclipses? Well, lunar phases are a consequence of the moon's 27.3-day orbit around Earth. Here's a very major misconception in astronomy, is that shadows cause the phases of the moon, and that has absolutely nothing to do with it whatsoever. The phases of the moon have to deal with the changing angle between the sun, Earth, and moon. We'll take a look at that. So the moon goes from new moon, which is when we can't see it at all. New moon rises at 6 a.m. and sets at 6 p.m., so we never see it. There's nothing lit that we can see. Half the moon is always lit at some point in time. We go through 4 main phases and 4 secondary phases. So the first one after new moon is, of course, first quarter moon. And the first quarter moon rises at noon and sets at midnight. Full moon rises at 6 p.m. It's seen all night long, sets at daytime in the morning at 6 a.m. And then third quarter moon, where the left side is lit up, rises at midnight, sets at noon. If you're going to class or going to work early in the morning and you see the moon out, it's probably going to be a third quarter moon. Now the secondary phases are crescents and gibbous phases. And so we have a waxing crescent. This is just a few days into the lunar cycle, and we see a little bit of a sliver on the right side. Waxing crescent. I always keep using the terms, you remember from the Karate Kid movie, wax on, wax off. If you wax your car, it gets brighter, right? So waxing crescent is a moon that's getting brighter and bigger and lit. And then we have waxing gibbous, which means more than half lit up, not all the way lit up. Past full moon, when we're starting to lose moonlight, we call those waning gibbous. So I always say, it's kind of silly, waning sounds like waving, so you're waving goodbye to the moon. And then the waning crescent, which is the end of the cycle. So it all has to do with the sun, moon, and earth, and the phases of the moon caused by that change in angle. So here we are, 29.5 day cycle for the phases of the moon. Now I said earlier it takes 27.3 days for the moon to go around the earth, but the phases are a little bit longer. And that has to do with the fact that the earth itself is moving in the universe around the sun. And so that extra 2 days is the fact that the earth has gone around the sun a little bit, and it has to go a little bit farther around to get back to its original spot. Alright, so what causes eclipses? An eclipse is a very unique situation with the sun, earth, and moon. We'll look at this first. We know the earth and moon cast shadows, and when either of them passes through the other shadow, we have an eclipse. And so there are 2 types of shadows: the penumbra, which is kind of a light shadow, and the umbra, which is a very direct dark shadow. So here are the possibilities for lunar eclipses. The moon goes through the shadow of the earth, and it casts this red glow onto the moon. Why would the moon be red when the moon's going through a shadow? Shouldn't it be dark? It's the same thing as kind of like watching a sunset, and the sun gets nice and red. The sky gets red. there's still light coming through the Earth because we have an atmosphere. And that atmosphere bends that starlight and makes it longer in wavelength, which means it gets redder in color. And that red hue gets cast onto the full moon. A lunar eclipse only happens during a full moon. In a solar eclipse, we have the opposite. This is when the moon blocks the sun from the Earth. And it just so happens, by coincidence, that the sun and the moon are about the same angular size in the sky, about 1/2 degree. And so when the moon blocks the sun, again we have a small shadow cast onto the Earth. And so this picture here is a picture of the shadow of the moon cast onto the Earth. Now, about a year and a half ago in 2012, there was a almost total solar eclipse seen from Las Vegas, and I will get you a picture of that. I went to Las Vegas and had my solar glasses on, and we were watching the solar eclipse from the Hard Rock Cafe. And people were like, "What are these weird glasses you have on? What's going on?" I said, "Oh, it's a solar eclipse. We're watching the solar eclipse." And soon all the guests came over and all the wait staff came over and wanted to see the solar eclipse, and we actually made such a fuss that we got our food for free that day. That was pretty neat. Now, solar eclipses only happen at new moon, and solar eclipses can be partial, total, or annular. Partial is the most common one, where the moon blocks out part of the sun. Total is the rarest kind, where the entire sun is blocked out. And then you can have an annular eclipse. I've seen an annular eclipse. Back in 1993 we had one. This is when the moon is just a little bit, doesn't quite match up in size with the sun, and it doesn't block out the entire sun. We have a little bit of a ring around the moon that we see the sun, just because it doesn't quite block it out. And we had that in 93. I have never seen a total solar eclipse, but we will see one in a couple of years in 2017. That's just 3 years away. In August, it'll go right through Springfield, Missouri. Very rare. Okay, if the eclipses happen at full moon and new moon, why don't we have an eclipse at every new moon and full moon? It's because the moon's orbit to the Earth is tilted 5 degrees. And so we have about 2 eclipse seasons every year, with a lunar eclipse at noon and solar eclipses at full moon. So, to summarize, 2 conditions must be met to have an eclipse. It must be a full moon for a lunar eclipse, or a new moon for a solar eclipse. And the moon must be at or near one of 2 points in its orbit where it crosses the ecliptic, the imaginary path of the sun, and we call those nodes. Now we can predict eclipses. Here we see that one, August 21st, 2017. This is going to be the one that goes right through, very close to Springfield. When we had in 2012, went right through Las Vegas. So we have learned that half the moon is always lit by the sun, half of it is in shadow, and its appearance to us is determined by the relative changing angles of the sun, moon, and earth. We know the eclipses are caused by the Earth's shadow on the moon, lunar eclipses, that's when the shadows come into play, or the moon's shadow on the Earth for a solar eclipse. Now let's take a look at the ancient mystery of the planets. What was once so mysterious about the planetary motion in our sky? And why did the ancient Greeks reject the real explanation for planetary motion? Well, in ancient times, we knew of Mercury, Venus, Mars, Jupiter, and Saturn. Those are the planets you can see with your naked eye. Mercury is very hard to see. It's always very close to the sun. It's only seen for maybe a week or 2 out of the entire year. Venus is very bright because it has a lot of thick clouds on it that reflect sunlight, and we call this the morning or evening star sometimes. Mars is red because of the iron on its surface. Jupiter is very bright because of also the thick atmosphere it has, and it is so huge. It's our biggest planet. And then Saturn is moderately bright. It's almost as big as Jupiter, but twice as far away. Well, the planets usually move slightly eastward from night to night relative to the stars, but sometimes they go westward relative to the stars for a few weeks, and we call this apparent retrograde motion. We see this with Mars on occasion. And so this retrograde motion is kind of due to the fact of the Earth's orbit being a little bit faster than Mars's orbit, and we catch up and go past them. Just like driving along the highway and you come up near a car in your other lane and you see them ahead of you, but you are going faster in your outside lane, so you see them actually going backwards relative to you and you pass them. Same thing here. Now, why did the ancient Greeks reject the real explanation for planetary motion? It was their inability to observe stellar parallax. Parallax is an apparent shift in position. And one good way you can check out parallax is to take your thumb like this and close one eye. I'm going to cover up my web camera with my thumb, and now I switch eyes to my other eye, and my thumb has appeared to move to the right. Has it really moved, or did the web camera move? Well, neither one moved, actually. It's the changing angle that my eyes are looking at my thumb. So it's an apparent shift. So the Greeks knew that the lack of observable parallax could only mean one of two things: that the stars were so far away that parallax is too small to notice with the naked eye, or that the Earth does not orbit the Sun, it is the center of the universe. And with very rare exceptions such as Aristarchus, the Greeks rejected the correct explanation, number one, because they did not think the stars could be that far away. And so this set up a long-standing controversy where the stage was set for a long historical showdown between Earth-centered and Sun-centered systems. So what was so mysterious? Well, like the Sun and Moon, the planets usually drift eastward relative to the stars from night to night. Sometimes for a few weeks or even a few months we see backwards motion called retrograde motion. Why did the ancient Greeks reject the real explanation for planetary motion? It was because most Greeks concluded that the Earth must be stationary, and because they thought the stars could not be so far away.